Well, hello. Welcome to the IC Flores Software Scientific Sprinkler Program, an engineering tool to better evaluate risk. I designed this program to save me valuable time, hours of manual calculations on sprinkler, evaluating sprinkler system. I visited a facility, Houston, Texas, and it's a robot work of occupancy. To save valuable video time, I enter company information, occupancy, enter sprinklers, distance between sprinklers and branch line, and distance between branch lines. I enter sprinkler K factor. I enter branch line to cross main and nipple length in inches. I enter sprinkler temperature. I also enter elevation and water supply test information, static pressure of 100, residual pressure of 80, and a flow of 1500 GPM. One of the first things you do to evaluate sprinkler system is to generate a sprinkler sketch when you visit the facility and use that sprinkler system to enter data in this program. Uh, um, I generated a sprinkler sketch and I'm going to bring it out so you can see the information. I'm going to click import my sketch, and here's my sprinkler sketch. I'm going to move it so you can see it. It's a centipede sprinkler system with 6 heads on branch line A, and we labeled the branch line as A, B, C, all the way down to P. And on the opposite end, I label as branch line AA, BB, and all the way down to branch line PP. These are the branch line, and the middle is the cross main. And this is the feed main, and we got some detail where the branch lines connect to this to the cross main. We have fittings. So we got a T, and this is the cross main, and we got a nipple, and that nipple is 2.5-inch diameter by 12-inch in length. We have a riser detail showing the elevation 18 feet. I'm sorry, 19 feet. We have 8-inch times 19-inch of riser, and we have some fittings, and you have an alarm valve and a gate valve. And it shows we also have fittings, a T, an elbow, and we got another elbow. And this is information about the occupancy in the sprinkler system. We have a robot work operation. The sprinkler system is an extra hazard. System type is wet, and again, distance between sprinklers, automatic sprinklers is 10 feet. Distance between branch line is 10 feet. Sprinkler cake factor is 8. Sprinkler temperature is 212 degrees. Here's my water supply test information, static pressure at 100, residual pressure of 80, and a flow of 1500 GPM. It's for ABC Company, located at 25 River Road, Houston, Texas. And I enter most of this information already into the program. Let's now also look at the sketch. The sketch shows a pipe size, 1 inch, an inch and a quarter, an inch and a half, and that's our nominal pipe size. And below it shows the distance between sprinkler head, 10 feet, 10 feet, 10 feet, 10 feet, 10 feet, and 5. And on the cross main, it does the same thing, shows the pipe size and pipe length. Let's enter remaining information. We're going to identify an extra hazard sprinkler system and identify the type of sprinkler system as being a wet pipe. So let's delete my sketch. We no longer need it. And let's continue entering information. Next place we got to go is to click density area chart. When we click that, this density versus area chart opens up. It shows area in square feet and the density in gallons per minute per square feet. It shows several lines: line hazard, owner hazard group 1, owner hazard group 2, extra hazard group 1, and extra hazard group 2. The sprinkler system is extra hazard, so it could be the density that we're looking for could be either 0.30 over 2500 or 0.40 over 2500. Let's click either the radio button or any place on the red line and a window opens up showing which occupancy classify as extra hazard group 1, and we're looking for robot work operation, anything involving robot. So we look down, and here's a robot cloth coating, robot working, and synthetic robot. So a robot work operation is a extra hazard group 1 occupancy. Let's click next. And when we click OK in this window, the density and operating area as well as host demand will populate the empty fields on the main screen. So let's click OK. And it did. It identified itself as an extra hazard group 1. It gave us a density of 0.30 GPM per square feet over 2,500 square feet. And it identified your host demand at 500 GPM. It shows the area per head is 100 square feet. It identified 25 heads that we need to flow in a hydraulically most remote area, and we need to flow 6 sprinklers per branch line. It identified the minimum head pressure as 14.1 psi. Let's continue. We go to the next cell, and we select the type of sprinkler system installed. We click system selection button. Windows open up where we could select one of 3 types of sprinkler system: a wet pipe, a dry pipe, or pre-action. A sprinkler system is a wet pipe, so we click wet pipe. And it type over here wet pipe sprinkler system, and identify the coefficient of 120. We done with the sprinkler selection. We click OK. And now we go to the next screen where the program will sketch a sprinkler system. So we click the sketch button. It's bring us to this blank screen. It's called a sprinkler sketch generator. It brings a window up. We could get some help if we need to clear any sketch that we may have. And it identified 3 buttons, so we could sketch a light hazard sprinkler system, an ordinary hazard sprinkler system, and an extra hazard sprinkler system. A sprinkler system is extra hazard, so we click the extra hazard button. And the windows up and out showing a center feed extra hazard sprinkler system. It shows 1 branch line, and it shows a maximum of the heads that we could have on an extra hazard sprinkler system. We could have 6. On the left-hand side, we call that branch line A, and 6 on the right-hand side, we call that branch line AA. Our system also has 6 heads, so we identify the heads that we have. 6 heads on branch line A, and 6 heads on branch line AA. You must click those heads, otherwise the sketch will not be generated. We click them, we click next, and now Windows open up, so we can select a pipe schedule. A sprinkler pipe schedule is schedule 40. We click it, and our sketch is generated. It shows 6 heads on branch line A. This is branch line A, B, C, D. It goes from branch line A to branch line L. And on the right-hand side goes from branch line AA to branch line LL. So this is a numbering and labeling sequence. It shows the pipe diameter between branch lines, and it shows a nipple diameter, 2.5 inches. And it shows the cross main, and the cross main connecting to the riser. Let's click my sketch again and see any difference between the two. In my sketch, we show some detail where the branch line connect to the cross main. We have this detail. We have some fittings. We have a T on the branch line and a T in the cross main, and it shows the diameter, 2.5 inches by 12-inch nipple, and it shows some elevations. On the right side detail, it shows where we have an elbow, where we have a T here, we have an elbow, and the length of the piping. And it shows some fittings, an 8-inch alarm valve and 8-inch gate valve. Now let's look at the sketch. We have a cross main and the feed main. The feed main connect to the cross main between branch line H and I. So let's make that change in our computer program by clicking the cross main and moving it up between branch line H and I here. So now my sketch looks something like the computer generated sketch. Let's X out. And now the computer sketch shows a closed head represented by a 0. And we need to open those heads by replacing the zeros with 1. But we're not going to replace every head. We need to replace 25 heads. Numbers of sprinkler flowing 25 heads. So we're going to open 25 heads by replacing the zeros with 1. We need to open 6 heads per branch line, but we need to do that on 5 branch lines. So let's begin. We place the cursor on the first 0 and replace that 0 with 1 by just typing 1 on top of the 0. 1. Press the tab key on keyboard. It takes you to the next 0, and you do the same. And press the tab key and keep doing it. As we replace the zeros with 1, there's a count going on over here. We have 3 heads that we replace the zeros with 1. We just basically opening 3 sprinkler heads. We need to open 6. So we open that 1. Go ahead and open that 1 and open 6. We open 6. We do not open 7. Do not open 8. We go to branch line B now and do the same thing. Open those heads. But we could save time by clicking the letter B or for branch line B. Click it and we'll open the same numbers of heads that it opened on branch line A. We got 6 heads open on branch line A, 6 heads open on branch line B for a total of 12. We'll do the same thing with branch line C and branch line D. We got 24 heads open, and we need to make this criteria. We need to open 25. Do not open 26 or 27. We need to open 25. So we open the one head on branch line E, and it should be the head's closer to the cross main, so we open that head. And we just open 25 head. We calculated flowing pressure from this first sprinkler to the last sprinkler. Actually, the calculation is made to the first non-flowing branch line. The first branch line that's not flowing is branch line F, and that's become our first non-flowing branch line. Let's highlight the heads that we open to show a hydraulically most remote area, and this is it. Click the tab key on your keyboard, and it shows the heads that we open. Now we need to calculate pressure drop from the first non-flowing branch line, which is branch line F, all the way down to the base of the riser. To here. Before we do that, we got to consider fittings. We have fittings where the cross main connect to each branch line, and it looks something like this. We have one T on branch line A, one T on branch line AA, and a T on the cross main. So let's select those fittings. We click the fittings button, and here is an illustration of what we have at each point where the cross main connect to the branch line. And here are the pipe sizes. On the branch line A, we have a 2-inch T. On branch line AA, we have a 2-inch T. And on the cross main right side, we have a 2.5-inch T. So let's get those fittings. We click T1, windows open up, where we could select the pipe diameter, fitting, and quantities of fitting. First thing we do is go to and select the pipe size 2 inches. On the fitting selection, we select standard T, and we select the quantity 1, and we click OK. Now we need to select this fitting that's identical to T2 is identical to T1, so we click T2. It's identical, so we make no changes. We just click OK, and we just selected the fitting for T2. Now let's select this fitting, which is a 2.5-inch T. Click it. We change the pipe size to 2.5-inch. It's still standard T in this one. We click OK. We just selected all the fittings for our sketch, our sprinkler system. We click OK. Now we need to calculate friction loss from the frictional flowing branch line, which is branch line F, all the way down to the base of the riser. And to do that, we go to sprinkler riser, we click the sprinkler riser button, and we come to this table. It's the center feed. It's a center feed riser data input, and it's the friction loss calculator from frictional flowing branch line to the base of the riser. We have some information that was already calculated and imported. It shows here that the flow is 900, the required flow is 943 at 52 psi, but that's at the frictional flowing branch line, right over here. We need to calculate now the demand at the base of the riser, and we could use this sketch to guide us, or we could go back to my sketch. From frictional flowing branch line, we have some pipe sizes. We have 5-inch, 10 feet of 5-inch, another 10 feet of 5-inch, and we have 5 feet of 6-inch. Half of this 10 feet goes from here to there, so that's 5 feet of 6-inch. So let's enter those pipe sizes. The sketch, the feed main and riser, we could click it and they are 8-inch. So let's first, before we enter this length, let's enter the pipe diameter. So we have 5-inch, and we enter data below the pipe diameter, and we enter that on a schedule 40, not a nominal pipe size. When we select the schedule 40, the program gave us this table, and that is schedule 40 pipe sizes. If we hover the cursor above, it shows the nominal pipe size in yellow and blue letters. So this is a 2.5-inch pipe. This is a 3-inch, 3.5, a 4, a 5, a 6, an 8, and 10. So let's copy the 5-inch pipe. We could type 5.295 or save time and just click equals, go to 5-inch and click enter. We just copy the pipe size. We do the same thing with the 6-inch. Go to 6-inch, press enter, and we do the same thing with the 8-inch, equals 8-inch. So we just selected the pipe size from the frictional flowing branch line to the base of the riser. Now we select the pipe length. On the 5-inch pipe, we have 10, 20. Went to 20 feet. On the 6-inch pipe, we have 5 feet. Let's look at my sketch to make sure. And here we go. A 6-inch, and it's between here and there. So that's from branch line H to I is 10 feet. We're in between, so that's 5 feet. So let's enter 5 feet of 6-inch pipe. And now let's look on the 8-inch pipe. On the 8-inch pipe, we have 60 and 80 and 19. Let's get the calculator and calculate that. Is the calculator, we got 60 feet plus 80 plus 19. We click equals, and that's 159 feet. 159 feet. Now let's look at the fittings. Let's go back to my sketch. On the 5-inch, we got no fitting. On the 6-inch, we have a T. On the 8-inch, we have an elbow. Let's look at the detail. It's another elbow. So we got two elbows. We got an alarm valve and a gate valve. So let's identify those fittings. On the 6-inch pipe, we have one standard T. On the 8-inch, we have two screwed elbow, comma, space, one alarm valve, comma, space, and one gate valve. Now, let's identify the fitting equivalent length. And we click the radial button next to the fitting. So we click this radial button. Windows open up to select the pipe diameter, fittings, and quantity. We change the pipe size to 6 inches. We have one standard T already pre-selected and the quantities of one. We make no changes. We click OK. Give us a fit equivalent length of 30 feet of 6-inch pipe. We go to the next fitting selection and we click the radial button next to it and Windows open up again. Now we change the pipe size to 8 inches and we select the fittings all at the same time. We have a screwed elbow, and we got two of those. We have one alarm valve and we have one gate valve. Gave us 110 feet of equivalent length of 8-inch pipe. Program added the pipe length to the fittings and it gave us a total length. And it calculated the demand at the base of the riser, 943 GPM at 66.8 or 67 PSI. Let's click calculate to make final calculation. No changes were made. And let's look at the summary. Hydraulic calculations. Here's hydraulic calculation summary. We open 6 heads on branch line A, 6 heads on branch line A and B, and the same thing on C, and 1 head on branch line E. It gave us the heads that we open a number, the flows are calculated, the pipe size is given, the fittings are identified, the length, the pipe length, the fitting length is shown, and the total length, and here's the friction loss, your minimum end head pressure, your pressure summary, and the total pressure. If you scroll down, it shows our demand, 943 GPM at 66.8 PSI, and the fittings we selected are here. On the 6-inch, we have a standard T. On the 8-inch, we have 2 screwed elbows, 1 alarm valve, and 1 gate valve. So that's also identified. And a table below shows a key for the fittings. We done the calculation. Now we could look at our linear graph. We click linear graph, and here's a linear graph. It brought over the company information, brought over the water supply information, your hose demand, your sprinkler demand, and the demand at the first node flowing branch line, 943 at 54 PSI. The density available is 0.35 with hose and 0.38 without hose. The required density is 0.30, and this is your sprinkler demand, your hose demand, and your water supply and your hose demand. Let's look at our lag 185 graph. Lag 185 graph is not generated. We need to generate that ourselves. The program is based on Excel 2003, and it cannot generate a lag 185 graph automatically, and neither does Excel 2013. So we had to go around that problem and invent ways to generate a lag 185 graph. So I generated a scratch pad it's a lag 185 graph, And we brought over information on on the water supply, your hose demand, your sprinkler demand, and density. When we enter information in this white boxes, it will calculate below your density with hose and your density without hose. Before we do that, we gotta plot a water supply. Our Lag 185 graph has two scales, a pressure scale and a flow scale. And you could go down or up on the scales and select an appropriate scale to plot the graph. I'm gonna select the pressure that starts with 10 psi. And we could do the same thing on the flow scale. Go up, go down, and I'm gonna select a scale that starts with 200 GPM. So 200 GPM, this is 1500, and we could now begin plotting our water supply. To do that, we have plotted, we have generated some buttons here. If you click supply, this is water supply, and our lines will drop. We got a line for friction loss, for pressure drop, for hose, for sprinkler demand, for horizontal pump, for vertical pump, and these are dots that you could put on top of this line. It's a pointer, a guideline, and labels. The other buttons in orange program buttons take us brings the menu so we could go back. Let's now bring a guideline to plot the water supply. Guideline drops into the screen and we could move it around. Some protected, we could size it. And we need to put it at 1580 to represent our water supply. So let's put it at 1500 on the flow and at 80 psi. We go to 80 psi and this represents a water supply, 1500 at 80. Let's bring a water supply line, one drops. We could again click it, pivot it, and we need to put it at 100 psi to represent a static pressure. So we put 1 point at 100 psi. The other end, we put it on a guideline at 1580. This represents a water supply. Now we could click it and extend it to the end of the graph, like so. From this water supply, we subtract 500 gallons for the fire department. So let's go to a convenient flow such as 2000, put it at 2000, go up to basically where you touch your water supply. And from 2000, we're going to subtract 500 gallons for the fire department. So you grab the opposite end of your guideline and go to 1500. 2000 gallons minus 500 is 1500. This becomes 1 point of our hose line. To plot a hose line or hose demand, you need 2 points. So let's grab another guideline. We click it and move it to a convenient flow such as 1000 gallons. And the other side of the point, we move it to 500. 1000 gallons minus 500 is 500 gallons. So we add a 500. And now we click the guideline and move it up till we touch the water supply, like we did before. So now we got 2 points to plot a hose demand. We click the hose button, line drops. We need to put 1 point right there on that guideline and do the same thing with the second guideline. So this now represents a hose demand. We click it and extend it to the end of the graph like we did with the water supply. And the opposite end, you extend it to zero flow. This represents a hose demand. We click one guideline and delete it. We only need one. Now we need to plot the water supply, 943 at 67. So we use the guideline again to go to 67 psi, 60, 65, and 67. It's around there. Don't have to be so precise. we need to flow, we need to put the guideline at 943 GPM. So let's go to, we are at 1,000. This is 900, we go to 950, and then subtract a few PSI. This represent 943, 67 PSI, and your sprinkler demand is right here. Let's grab a sprinkler demand line, click the sprinkler button, and a line drops with a pointer. Let's click the pointer and put it on top of the guideline to represent our demand. Click the guideline and put one end at zero flow and zero pressure right at the corner of our graph. Grab the opposite end and put it on top of a pointer. This is our sprinkler demand. Now we could grab it and extend it past the water supply line. This point represents our demand, 943 at 67, and it's also equal at a required density, 0.30. So we could label that point. Click label drafts, and you on top of it just type 0.30. The label cites itself based upon what you enter, and you could click it and drag it to represent a density. You could put it on any place you want to. Put it right here. The required density is 0.30 at this point. Now we need to identify the flow where the hose demand touches your sprinkler demand, and also where the water supply touches your sprinkler demand. So we could calculate density available with and without hose. So let's grab the guideline again and put it here. And the other opposite end, put it here. Let's get 2 pointers to identify those points. 1, 2. Is one. And here is your second point. Now let's identify those flow. Where the hose line connect to the sprinkler line, follow the guideline down, and it's somewhere between 1,000 and 1,100, but not quite 1,150. It's more like 1,140. So go to the hose intercept and enter 1,140. And the density available at that point is 0.36. Let's identify the flow. Let's make final adjustment on that pointer. Let's identify the flow. Follow the red line down, and it looks like 1110. So on the supplied intercept, enter 1110. The density of 1110. Density available is 0.35. Density with hose, 0.36. Density got something wrong there. Hose intercept is 1040, not 1140. So it's 1040. That's better. Density at this point is 0.33. The density at this point is 0.35. So let's label those points. Get the label. Type 1 0.33. Grab another label and label that 0.35. Let's grab a guideline and delete it. We no longer need it. Thank you, guideline. Now we label the lines. The water supply. Type supply. We could type water supply or just supply. Supply is sufficient. Drag it and put it on top of the water supply. Grab another label and label the hose line. Hose or hose demand. And we do the same thing with the sprinkler demand. Call that demand. And we're done. Let's now go back to our linear graph. The linear graph shows different density. We could bring the densities from our lag 185 onto the linear graph just by clicking this button. When you do that, it shows the density based on lag 185 and the label change over here. Density available based on lag 185 graph. Let's see again the density available based on linear, and that's 0.38. On lag 185, it goes down. The lag 185 is more accurately, and that's why we use. So let's go back to our main screen. We're done. Click menu button, go to select a form, and here a linear graph is shown with lag 185 densities. On top, it shows protection adequacy based on lag 185. It shows the density needed 0.30 over 2500. Density available with host is 0.3 over 2500. Density available with our host is 0.35 over 2500. And over here it says protection is adequate. The computer made the calculation, determine that protection is adequate as the density available is greater than the required density. It shows the operating area. And now we could bring our lag 185 graph and put it in our main screen. Just click lag 185, and here's our lag 185 graph. You could click it and make it bigger to show a copy of our lag 185. We could delete it and bring it back again. There we go. We could print this information. Print the main screen. We could click close, and the next screen we could print it just by clicking print. Close, and the next screen opens, so we could print it. Here's the hydraulic calculations. Here's your lag 185 graph based on linear graph using lag 185 densities. So the lag 185, the linear graph is as accurate as the lag 185 graph. And if you close it, here's a lag 185 graph, and we're done. I save a lot of time by using this program to evaluate adequacy protection. Many times I have to evaluate 5 systems in a facility that I visit. So it takes more than 10 hours to evaluate sprinkler protection. Using this program, you could take about 4 minutes per sprinkler system. This program is for sale. If you're interested, you could send me a message. My email is shown in YouTube. Next to program detail. I thank you for viewing this program.